Welcome back to our heat transfer class, where we're delving deeper into the one-dimensional, steady-state heat conduction. This video was made with the support of Energy. The topic of one-dimensional steady-state conduction is divided in several lessons. There is at least one video for each lesson. Let's continue with the seventh one. This lesson is divided into several parts. As in many cases in the heat transfer topic, we must start defining a differential control volume and making the energy balance. In this case, the differential control volume length is differential of x. Please notice that for a fin of constant cross-sectional area, the perimeter is also constant. Because we make the analysis in steady state and without internal heat generation in the fin, inputs should be equal to outputs. Let us look at the section in two dimensions for simplicity. The heat input is the heat that arrives to the control volume by conduction through the fin cross-section. If the fin is at different temperature than the surrounding fluid, there is heat transfer by convection. Finally, the heat that is not transferred to the surrounding fluid goes across the control surface in the tip direction by conduction. After the identification of heat transfer mechanisms for inputs and outputs, we can write the conservation equation. We can write the heat transfer rate at x plus differential of x as the value at x plus the derivative with respect to x multiplied by differential of x. Substituting in the energy conservation equation. After that, we can apply de Fourier's law for conduction and the Newton law for convection. The result is a differential equation where dx can be simplified. In this way, we get the general differential equation valid for all fins with one-dimensional conduction. Notice that this differential equation is different than the diffusion equation inside a solid, the Laplace equation for one-dimensional steady-state conduction without internal heat generation and constant properties. The procedure to find temperature distributions and heat transfer rates will be the same than the one used for the diffusion equation. To simplify the form of this differential equation, we transform the dependent variable by defining an excess temperature theta as the difference between the fin temperature and the fluid temperature. The derivative of theta is equal to the derivative of t respect to x. The same for the second derivative. Substituting the temperature by the excess temperature, the result is a linear, homogeneous, second-order differential equation with constant coefficients. Obviously, when h, lambda, p and s are constant. The parameter m of a fin is, in some way, a ratio between the heat transfer rate by convection in the surface divided by the heat transfer rate by conduction across the fin. Solving this equation, instead of finding t, we will find the solution for the temperature excess theta. The linear, homogeneous, second-order differential equation with constant coefficients has a general solution. We need two boundary conditions to find C1 and C2. After finding the temperature distribution along the fin, we will be able to find the rate at which heat is transferred by convection from the fin. To evaluate the constants C1 and C2 of the general solution for the theta function, it is necessary to specify appropriate boundary conditions. One such condition may be specified in terms of the temperature at the base of the fin. The second condition is specified at the fin tip, that is, for x equal to LF. It may correspond to one physical phenomenon in the tip. In this course, we will study only four. The most common condition is A, where the fin tip dissipates heat by convection. At the tip, Fourier's law equals Newton's law. Condition B assumes no heat transfer at the fin tip. Applying Fourier's law at the extreme, if the heat flux is zero, the derivative of theta is zero. Condition C implies that the end temperature is prescribed. This case is not actually a fin but a thermal bridge between two solids. Condition D is an ideal case in which the length of the fin tends to infinity. In such a case, the tip temperature tends to equal the fluid temperature and theta tends to 0. This is an unreal case, but it is mathematically the simplest, so we will start by studying this case. How does the temperature distribution look like for a very long fin? The temperature distribution is an asymptotic curve where the fin temperature approximates the fluid temperature at the infinite. As consequence, C1 is 0. The other boundary condition is that for x equal to 0, the excess temperature is theta 0. Applying this boundary condition, we find the excess temperature function. And from this, the temperature distribution along the fin. Let's analyze now the expression and relevance of the m parameter. Recall that the m parameter is the result of grouping several parameters in the differential equation of a fin. The m parameter depends on the convection coefficient and the thermal conductivity of the fin. However, let's analyze the ratio between the perimeter and the cross-sectional area. For a cylindrical fin or pin, the ratio of the perimeter to the cross-section is equal to 1 divided by 1/4 of the diameter. Straight fins of rectangular section that go along the heat exchanger. These fins are usually very long and there is no contact with the fluid in the front and back surfaces. This is the reason why the wet perimeter is only 2 times the depth W. The cross-sectional area is the rectangle TF times W. For these fins, the ratio of the perimeter to the cross-section is equal to 1 divided by half the fin thickness. Therefore, the parameter m can be calculated without knowing the fin depth W. Let's analyze the temperature distribution of a very long fin for different values of the parameter m. For very low values of m, the temperature of the fin remains very close to the temperature of the base. If what we want is to dissipate the maximum heat, it is important to keep mf small. If mf is very large, the fin temperature decreases very fast. If what we want is the temperature to dropping quickly, for example in the handle of a frying pan, mf must be high. Finally, let's see what are the solutions for the temperature distribution for the 4 boundary conditions. In this video, we have found the temperature distribution for the infinite fin, which is the easiest mathematically. For the adiabatic tip fin, the temperature profile depends on the product of m times Lf. For a fin with prescribed temperature in the tip, the temperature profile depends also on theta L. The more complex expression is the one for the fin with convection in the tip. The next step is to calculate the heat transfer rate for these 4 temperature profiles. Watch the video about fin's heat transfer rate to know how to find it by applying the Fourier's law and the Newton's law.